Hi everybody, my name is Craig Maynard. I'm a FIRST Robotics Senior Mentor and I'm an instructor of robotics and automation at St. Polytechnic. And I'll bet you want to use pneumatics in your robots. So in order to use your pneumatics effectively, I'd like to give you a little presentation on pneumatics and some of the basic parts of pneumatic systems. And in the next video, we'll talk about how to actually implement those pneumatics in your first robot. So I want to start talking to you about how pneumatics are used mostly in industrial systems or factory systems. And I'll skip through this because it's really not relevant to you. Let's get this thing going again here. Now, pneumatics, of course, is the principle of using compressed air to power your actuators in your robot. There's lots of reasons to use air. Number one, it's easily available, it's freely available. It's composed of a number of gases, as you probably know from your chemistry classes. It's 21% oxygen, 78% nitrogen, 1% trace elements. But the most important thing about air is that it contains a lot of water. And we have to be very careful when we compress air because that water gets squeezed out and forms a liquid inside your pneumatic systems. And that liquid can mess up your pumps, it can mess up your valves, it can, if you have metallic parts inside your system like metallic tanks, it can rust those as well. So you got to be very careful that you do maintain your systems and don't get any air or water in your lines. That can happen. So every once in a while you have to bleed out your tanks just to make sure that the water doesn't damage things. Now pneumatics it's a fantastic element. Pneumatics is basically any device that uses compressed air and exhausts it to the atmosphere. Pneumatics is the study of fluids. Fluids also includes hydraulics, but hydraulics, you don't want to exhaust that back to the environment. You keep that in a closed system. But pneumatics, you can compress the air, and when you're done with it, exhaust it back. In our FIRST Robotics, we don't like to use more than about 65 pounds per square inch for our systems. 100 pounds per square inch is usually adequate for most industrial applications, 110 psi. And the little FIRST Robotics compressors can do about 110 psi. But you can get up to 250 if you want to. If you talk about things like air pistols, those can be considerably higher, thousands of pounds per square inch in those guys. They got 6 basic components that you have to worry about in pneumatics, whether it's industrial or just in FIRST Robotics. The first thing is you got to have some way of compressing your air. Now, in FIRST Robotics, we use the little air compressor that comes in our kits. That's our pump that compresses the air and generates it. Now, in industrial systems, they also compress other things like steam. Well, they provide steam and refrigerants and heating and things like that. So the air compressor very often is in some kind of a common plant in a factory, some kind of a common building, a powerhouse, right? This is an example of a large compressor. You can see the electric motor right there that drives the big tank, the big reservoir on the bottom that drives it. And there's the air tank right there. You need to have some kind of a piping, of course, and that piping has to carry the air throughout the system. And the piping is usually, in FIRST Robotics, is usually a metric system, which means the pipes are usually 4 millimeters or maybe 6 millimeters across. You have to be very careful with that pipe. So when you do cut the pipes, you have to make sure that that end of the pipe is very, very straight, very almost 90 degrees to the length of the pipe, flat on. Any angles or any roughness in there is going to cause problems with the connections to your quick connects. So here's a little blurb on air sources. And I think we'll just maybe skip past this video and we'll move on to the next part just to expedite things. There we go. The next thing, now that you've got your compressed air in your pipes, is you have to have valves. And the valves are the devices that are used for controlling the air. They turn air on, they turn air off, they allow you to direct air from one pipe to another pipe to get the job done. They can do other things too. They can reduce pressure. They can reduce flow rate. You can have flow restrictors and things like that. So you have to have valves and actuators. The actuators are the cylinders, the pistons that actually move in and out to get the job done. Or there might be rotary actuators. There's all different kinds of actuators for pneumatics. But the most common ones we play with are cylinders or pneumatic actuators, pistons. So using air has a lot of advantages in your robotic systems. The first thing is it's very low cost. It's quite cheap. You can get good pneumatics from stores like Princess Auto and those kind of devices, places that are very robust, inexpensive, and easy to come by. So pneumatics is pretty cheap. Pneumatics has got a lot of different kinds of control systems out there. The actuators, there's also timing elements, there's pressure control elements, there's all sorts of sophisticated devices that make working with pneumatics a lot easier. We don't need those in FIRST here. We just need basically some valves and some actuators and maybe some flow controls and things like that. But they have a lot of different kinds of devices available for pneumatics. Pneumatics is very simple as far as moving parts and complexity goes. There's only one part that moves, basically. It's the cylinder. Goes in, comes back out again. Makes it very simple. And motors are very complicated. They've got a lot of moving parts. Servos have a lot of moving parts. Electrical linear actuators have a lot of moving parts. Pneumatics, pretty simple. Very, very basic, robust. Other advantages of pneumatics is they work under a wide temperature range. They work in hazardous environments where sparks or ignition could cause explosions and things like that. Well, you don't want to have motors; they make sparks. But if you're in an environment that has explosive gases, pneumatics won't make any sparks, and again, it's much safer to use. Some of the cons of pneumatics, though, is that they're easily compressed. They're quite spongy. It is air. It does compress. Hydraulics doesn't. Hydraulics is a very, very strong, tight kind of a medium, but pneumatics is kind of spongy. There is a risk of line leakage, of course. There's a extra care required if you want to have fail-safe. That means if you want to make sure that your system has got safety systems in place, so the pneumatics won't hurt you. You got to be very careful because pneumatics can be very powerful. So you have to make sure that your system is safe. And in FIRST Robotics, we do a lot in our pneumatic systems to make sure that the system is safe. And of course, being a pressurized system, it can be dangerous. You have to use safety glasses around pneumatic systems. Anybody in the area of the robot that has a pneumatic unit on it should be wearing safety glasses. Parts can fly off. The tanks can explode. Shrapnel can be projected at very, very high speeds. Even the compressed air itself, if it blows into your eye, it doesn't take much air pressure from a hose to actually cause corneal damage or damage to the eye itself. So you've got to be very, very careful when you're working with pneumatics. Pressurized systems can be really dangerous, so to always take care when you're working with your FIRST Robotics pneumatic systems. Now, air forced, here's a little blurb on pneumatic safety itself. Air actually forced through the skin can cause air embolisms. You can have air actually go inside your blood vessels, and these can transit through your system into your heart, into your brain. It can cause strokes. It can cause all kinds of horrible, horrible problems, including death. I've seen people play around with putting hoses in their mouth, and they turn the air on. Well, that's incredibly dangerous. Inflation injuries in the intestine can be caused by air being directed into body areas. So you could easily cause damage to yourself by putting this hose in your mouth and turning it on. Air blown in the mouth with only 5 pounds per square inch. It's very low. Only 5 pounds per square inch can rupture your esophagus, can rupture your lungs. So when you're working with air, it may seem harmless and it may seem fun, but it is a very serious power device, and it can be very dangerous. So be very careful. Eye and ear injuries can occur from flying objects and particles. These kind of ear injuries can cause partial or total loss of hearing. The hissing that comes from a hose is also very loud. That hissing can reach 120 decibels. Occupational Safety and Health Association doesn't recommend any more than 90 decibels before you have hearing protection. So that hissing from air sources can be very damaging. Put the hose in your ear. You can blow out your eardrum from up to 4 inches away. And it can actually cause brain damage. It can go right through blow your whole ear right out and cause damage to your gray matter. 12 pounds per square inch can pop your eye out of a socket. That's always fun. And of course, there's always the flying particles. They can cause bruises and cuts and contusions and all kinds of stuff. So, be very careful when you guys are working with pneumatics. That being said, if you are careful and you use your safety glasses and you respect it, it can be as safe as any other kind of a medium, electrical power, other things like that. They do recommend that you don't recommend using cleaning with compressed air. You see people that use compressed air for blowing off tables and cleaning dust off the floor and things like that. In many Canadian jurisdictions, cleaning with compressed air is not allowed. Specifically, compressed air shall not be used to clean clothes or other materials. So if you have a compressed air tank and you're using it to spray off the junk from your clothes, it's not recommended. It's just not recommended. Okay, so let's have a look at some of the pneumatic components that you need to work with. We're going to start with the ones that are used mostly in industrial. Now, this is a little video here. I won't show it right now, just to keep things moving. But this is a BattleBot video, and in this one, you would have seen pneumatic flippers getting underneath other robots and throwing those robots in the air, just to demonstrate just how powerful pneumatics can be. And of course, it's going to be just as powerful in your first robot. First thing we're going to look at are pneumatic pistons, and here's a few examples of pistons. A lot of people we call them cylinders. Actually, the piston is the little is the little object that moves back and forth inside the cylinder when you push air on it. So when you push air into a cylinder, the piston moves the shaft and moves the whole end effector. So technically, these are actually called cylinders and not pistons. Piston is part of the cylinders. Okay, you see the cylinder is a metal rod that extends and retracts in a pre-manufactured stroke, and you can see right there. There's the metal rod going back and forth, and you see the piston itself that moves back and forth inside there. Now, there are several kinds of pistons in there. The simplest one is called a spring return cylinder. And the spring return cylinder has only got one air port. You can see it on the right side right there. And that air port, when it goes in, pushes the cylinder out and extends it. When you release the air and the air is allowed to escape out at that port, then the cylinder retracts under spring control. So there's actually a small spring in there that allows it to retract. Those are single acting cylinders. A double-acting cylinder doesn't have a spring in it. A double-acting cylinder has got two air ports. You can see in the schematic here, there's an air port on the left side and an air port on the right side. If you put air on the left, it extends it. If you put air on the right, it retracts it. So this is a double-acting cylinder. In this case, you would need to have a double-acting valve to control it. With the single-acting cylinders, you just need a single-acting valve, one that just provides air and then allows the air to return through the same hose when it's turned off. Okay. Now this symbol right here, this is called it's a double-acting cylinder with the two ports, but it's air cushioned. So if you look on the cylinder itself, you can see that there's air cushioning on it. Those little boxes on the side there slow the cylinders as they get to the end of their travel. So rather than having the cylinders ram hard against the end of their travel, they will actually slow down with kind of a compressed little air shock on the end. And that little box attached to the piston in there, the boxes on the left and the right side of that piston, are involved in that air cushioning. And there's an example of another symbol with air cushioning on it there, and there's a cylinder. You'd have to actually, if you pull that cylinder out by hand, you would notice at the end of its travel, it kind of has a cush to it, a little, like it lands in a soft cushion, air cushion. So those are, in most cylinders nowadays, they have some form of air cushioning. A lot of cylinders also have magnetic cores inside them. So if you look in this piston part of this, you'll see a third box in the middle. And that third box is a magnet. And that magnet uses well, as the cylinder moves in and out, that magnet can be read by magnetic sensors on the outside of the cylinder just to determine if your cylinder is retracted or extended. That's called a magnetic core cylinder. Okay, cylinders are the most common actuators. We're going to leave those for now. Let's talk a little bit about valves. Now, valves are the devices that are going to be used for controlling the cylinders. I've got a few different kinds of valves right here. You've got some valves that are going to be provided for you in your kit of parts to help you with your cylinders. Let's have a look at the way valves are handled. The first valve we're going to look at is the simplest valve, and this is the schematic for it. It's called a 3x2 directional control valve. And you see, there are 3 ports on this. Each port is given a number. The number 1 port is nearly always the air intake. So the number 1 port is where the air comes into the valve. The 2 port is usually connected up to the cylinder. And number 3 is exhaust. So when the cylinder is retracting on it, let's say the spring is pushing the cylinder back, 3 is where the exhaust would actually come out of. Just going to see if I can bring up some pointer options here. Pin, there we go. So that would be the exhaust. So, and pin number 1 would be your air intake. So you notice there's 2 boxes here. There's this box right here and this box right here. This is because this cylinder, this valve, has got 2 positions. This is the first position, and you can see by this little T connector right here that it's blocked. No air can get in. This valve is not letting air through. Now, when you operate the valve slides over to the other position. And you can see now from port 1 right here, from port 1, the air can now flow through out to your cylinder. So if you had your cylinder attached down here, let's just say your cylinder was attached at this point, and there's your cylinder, and it's a spring return cylinder like that, and there's your port input. The air would flow in, and it would push the cylinder out. Okay. So back there it would be retract. It would retract. If this was your cylinder right now, and let's assume it was pushed out, you can see right here it's pushed out. When it's connected up now, the air would actually retract and be exhausted out port number 3, and that would allow your cylinder to retract. So that's why it's called a 3x2. There are 2 positions. There's this position. And there's this position, and there's this position, and there's 3 ports. So it's a 3x2 way directional control valve. And here's an example of a 3x2 way directional control valve. This has got a spring return on it, and a push button on one side. Oh, let's not do that now. Yes, always good timing with those updates. So you can see here, 3x2 directional control valve as before, but you got a spring over on this side. And this symbol right here indicates there's a push button. And this is what our push button looks like in the robotic labs at SAIT. We push this button and this valve goes in against the spring, right? So here it is this is in the pushed position right here, and this is in the released position down here. So you can see it's got 2 positions. This will be a manually operated valve. Now, a lot of the valves we have in FIRST are electrically operated. They're solenoid operated valves, so they don't use a push button. They use an electrical solenoid controlled by a Robo-Rio. So here's how a valve would look hooked up to your actual piston or cylinder. You see right now the air source. The air source is right down here at the bottom. You got an air source at the bottom, and it's going in. It's plugged at port 1. It's plugged right there. Excuse me. And the air can't get in to the cylinder. When you press the button, the air is now free to pass through that cylinder and through the valve, I should say, and into the cylinder out from port 2, and fills up the cylinder and ejects it. Now, if this air pressure was 100 pounds per square inch, let's say the air pressure was 100 pounds per square inch, and the surface of the cylinder right here, the piston surface was, let's say 1 square inch. I'll just say 1 square inch for that surface area. There would be 100 pounds of force pushing out on that piston. Okay, and of course, the larger that piston would be, the bigger diameter it is, the more force it would have. So you can get a significant amount of force out there. All right, so now the cylinder is extended, and when you retract it, when you release this button and let it retract. Oops, I think we did this one. When you let it retract, in this situation, the spring would move back in this direction. The air would now flow back through port number 2 again, but this time out port number 3 and exhaust air. Now, if you don't have a way for this air to exhaust through, the cylinder won't retract. It'll just stay at its extended position. So we have to make sure that there is an exhaust port available, and that's what port 3 is. It's the exhaust port. Okay, so that's extending this cylinder. Now, if you go to www.logiclab.hu, there's a little exercise for you on there. You can quickly learn how this works. It's absolutely free, and it's a great little simulation, and it'll allow you to take an air hose and plug it into this what's called a manifold, and all of these quick connects right here would allow you to connect onto your devices. Now, these quick connects are very clever. What you do with the quick connects is you take the hose that you have and you push it into the quick connect, and the quick connect will actually seal that hose into it, and it makes an airtight connection. To get that hose out, you have to actually pull on the blue part of the quick connect. You pull on the blue part while you push on the blue part while you pull on the hose, and the hose should pop out. Never ever yank that hose out hard unless you're pushing in on the blue ring on the valve, on the quick connect right here, or you'll damage the quick connect. But you can plug these hoses in and remove them as often as you want. They've got a great, very tight seal. Anyways, what you'll be doing here is you'll when you go to this website, you can hook up the hose here, and then you bring the hose over to port number 1 on this push button, and then port number 2, you'll bring a hose up to your cylinder. This is a single acting spring cylinder, so spring return cylinder. Then when you operate your air, turn your air on, which is this valve right here. This is the main valve for turning the air on, and it will cause the cylinder to extend. And then when you release the button, it will retract. So you push the button, it extends. You release the button, it retracts. Okay. So this is a 3x2 way push button valve with spring return, but it's normally open. So you can see if you, in this particular case, the button hasn't been pressed. You haven't pressed the button, but you have a path for airflow. So now your cylinder is going to be extended right here because the air, and I'll put a little spring in there, because the air is now able to go into the cylinder cavity and extend it. When you press the button, then it will retract. So this is called a normally open connection. This is called a normally open connection. Now this is a 3x2. Again, as you can see, it's got a spring return just like before, but it's got a roller lever on it. And this is meant to be impacted by an object. So if you want to have a panel or an actuator or maybe even another cylinder control your valve, you use a roller lever. So that means an object like this might be a door or something like that has come down and pushed this valve in. It's operated by a piece of hardware. Okay, and there you can see an example of the cylinder extended and operating this valve. Okay, and there you can see this is the whole cylinder right here with the valve being operated by this roller lever, and there's a close-up of it right there. You can see it being operated by the valve. So those are called roller levers. Those valves aren't meant to be operated by hand, as I said. They're meant to be operated by a machine, by a mechanical device. Okay. The idle return roller levers, if you have one of those in your kit, these only operate in one direction. They only operate in one direction. In the other direction, they actually hinge back. So if you could imagine, if you hit it this way, the roller lever operates. But if you hit it this way, the roller lever folds, right? So if it doesn't work that direction, it only works this direction. That's how a roller lever with idle return is meant to work. Okay, and there's another example right there of a idle return or a one-way trip. The symbol for it, you can see right here. This is the symbol for it on your pneumatic schematic diagram. It's a little bar that indicates it only operates in one direction. It doesn't operate in the other. So here's this little bar represents maybe one limit switch roller lever, and this one represents a second one, right? One is at the one end of the piston's travel, the other one's at the other end of the piston travel. And there's a couple more pictures of some roller levers with idle returns. Now, you may have noticed there's a number of different ways of actuating your push button on your schematics. When you take your 2x3 or 3x2, you can add on all these different shapes on here. This is a lever. These are push buttons. A general purpose actuator. This is a push button. Oops. Go back again. This is a pedal control, a foot pedal. This is the roller lever control. So all of these symbols here, there's a spring. All of these symbols here refer to the actuation techniques that are used in the push button. Okay, now I mentioned before that sometimes cylinders have a magnetic sensor on them, and that magnetic sensor in the middle here can be used to determine if the cylinder is in or out. So in order to use that, you have to have some special devices. So these are special pneumatic elements that you can put on your cylinder itself, and these will actually operate. In this case, this would be the operating one because the cylinder, you can see, is retracted. So that means the magnet that's on the piston is at this end right now. If the cylinder was extended, the magnet would be on this end, and this valve here would be operated. Okay, and this is the symbol for a 3x2. You can see the basic 3x2 control valve right there. It's got a spring return, and this is the symbol for a magnetic sensitivity, a magnetic pilot. That's what that indicates. You may or may not see that in your robots, but it's a very, very useful way of telling if the cylinder is extended or retracted. The next valve we're going to look at is a 5-port 2-position valve. And this valve is essential if you're going to have a cylinder that's a double-acting cylinder that doesn't have a spring return. So the 5-port 2-position valve, you can see right here, there's the 5 ports. Port 1, again, port 1 is the air entry. So if you had an air source, a triangle is a symbol for an air source, you would plug it into port 1. And right now, the air would be going out of port 4. So if you had a double-acting cylinder, and I'll see if I can sketch one over here. There's a double-acting cylinder. There's the piston inside it, and I have a port to retract it, and I have a port to extend it right there. You would hook up this one to the extend port, and you would hook up this one to the retract port. And now the air pressure would be going through 4 and retracting the cylinder. If you push the button, if you slide it over to the other operating position, there's the second part of the 5x2. Now, and I'll redraw my cylinder, and there's my retract, and there's my extend port, and we still have the air coming into port 1, and this is connected to 2, and this is connected to 4. Now the air is flowing through port 2. It's filling up this area here and pushing the cylinder out. And as it pushes the cylinder out, it retracts. The air escapes through 4 and exhausted to the atmosphere in 5. Right? So a double-acting cylinder. Now the cool thing about the double-acting cylinder versus the spring return is that it's powerful in both directions. It's powerful in the extension, and since air is pushing it back, it's powerful in retraction too. The spring return is only as strong as the spring in its retraction, and that might not be really, really powerful. Now when you look at this thing, there is actually slightly more power and extension than retraction, because retraction has got the surface area of this piston right here is reduced by the rod. So the rod is going to take away a little tiny bit of surface area on the retract side. You've only got this part and this part to push against. So it's a little less power on retraction than extension, but not much less. Okay, so if you go back to www.logiclab.hu, you can wire up this. So basically, you'll be taking an air hose, connecting it to your manifold. You should be able to go into any port on the manifold if it's programmed correctly, and then put this into port number 1. Port number 2, we'll put that on the retraction side, and port number 4, we'll put that on the extension side. And now, if you push this button, the cylinder will extend and retract. Don't forget to turn on your main air in order to make this work. So you push the button, you can get this to extend and retract. So I encourage you to go to this website right here and try out that simulation, see if it works for you. Now, up till now, our valves have been operated either by a thumb switch, right? They had a little symbol like this on the end, and you could operate it with your thumb, or they've been operated with some kind of a roller lever, perhaps a little roller lever like this on the end that allows it to be operated by a door or something like that, or a spring return. Might be operated by a spring return like you see right here. This valve is being operated by air. So you can have valves being operated by other air circuits, which is very convenient. In this case, when you operate this valve here, this will push, the whole valve will push to the right. It can push itself to the right. And right now, you can see that port 1 is connected up to port 2. So again, you might have it in a double acting cylinder like this. There's a port here and a port there. And when you operate the valve, when you operate this valve, air will be, and it slides over, air will go into this side right here and extend the cylinder. And when you retract it like it is right here, air is going into this side of the valve, the right side, and will retract the cylinder. So this is a 5x2 pilot, pneumatic pilot. So we're using air to control the valve rather than push buttons. And there's an example of such a valve. You can see right here, the way this would be wired up, or plumbed, I guess, is you would have your cylinder. I'll just draw a quick cylinder right here, and I've got my 2 ports on it, this port and that port. You would hook this up to the first port. This would go to the return port of the cylinder, and this would go to your main air. So wherever your main air source is, that would be, you see it says number 1 there. This would be your main source in. And this would be hooked up to a valve that controls it. So air coming in here would operate this valve. Okay? So this is called a pneumatic pilot spring return. This is if you want to have an air circuit control your pneumatic pilot. Okay? So this first one we looked at was a, there we go, was a spring return. You can see there's a spring return on this side right here, and air operates it. There we go. Oh, where have I gone? Sorry about that. There we go. This is a dual pneumatic pilot, so air extends it and retracts it. So the air actually forces it one direction or forces it the other direction. And if you operate this air right here, it will push it to the right. It'll push it to the right, and it will stay to the right. It will not fall back unless you operate 12. You take the air off 14 and you operate 12. Then it'll push it back. Now, the interesting thing about, they also call these memory valves sometimes because they hold their last position, they memorize it, or they call them shuttle valves. These are shuttle valves because they shuttle back and forth and they stay in their last position. And you'll notice there's a number on here, number 14. Well, that's kind of a hint. It's the port number, but it's also a hint that tells you when you operate this, port number 1 is going to be connected to port number 4. Because you can see the valve, the way that the air gallery is designed right here, it's slid over, so port number 1 will tie into port number 4. If you operate the right side, 12, then you can see port number 1 is tied to port number 2. So port number 1 is tied to port number 2. So that's kind of a little pneumatic device you can use to help identify those particular valves, 14 and 12. And there's a bistable valve right there. So again, if you had a cylinder, got yourself a lovely cylinder right here with 2 ports in it like this. You cook the ports up like that. Another port over here. This is the air that would control it in one direction. This is the air that would make that valve go the other direction. And this is the main air in. This would be your main air source, your 65 pounds per square inch or your 100 pounds per square inch. Okay. This is a 5x2 that has a detent, which means that when it operates, you operate it manually, but when you operate it, it stays operated because there's kind of a little detent on it. This is kind of what it looks like in our labs at SAIT. You operate this one way, and this switch will actually stay in that direction. So if you move this direction, it stays that way until you physically click it back. So it's got a little click in it, a little detent. That's what they call that. And that's that symbol right there, the detent. Okay, and so all different kinds of valves out there. We've only covered the most important ones and the ones that are actually in your FIRST Robotics kit of parts. But you can see there's a wide variety of different valves. There's all different ways of actuating them. You can actuate them electrically. You can actuate them with DC motors, with pulses, all kinds of ways of actuating your valves, which I'm not going to get into in this particular talk. Combined actuations. Another thing you'll actually see quite a bit in your schematics are these T-fittings, and the T-fitting is simply a way of bringing in 3 hoses together, right? So basically, there's nothing inside there; it just ties them all together. So air going in goes out in all directions. A couple other little special valves I'll talk about, which you don't have in your kit, but it's kind of good to know since we're having this little chat anyways. I may as well tell you about it. This is called a shuttle valve. Now, the way the shuttle valve works is air flows into port number 2. Port number 2, or air will flow out of port number 2 if either air comes in from A or from the left side or from the right side. So if air comes in from the left side or the right side, you will get air out A. If you have it only coming from one side, that little ball gets pushed over to the left and plugs up the left side. So you can see right here, the air actually won't continue through because it's plugging up that side. If the air comes in this way, then that little shuttle valve goes over here and plugs it up. So this is kind of like an OR gate. Either in through the left or in through the right will make the air come out. That's a shuttle valve. And there you can see a little animation of it. Air comes into the left, blocks the right side, and is able to escape out to the port 2. And it can't get in the right side. This is called a dual pressure valve. Now this valve here is used as kind of an AND gate. For this valve to work, for you to get air out of 2, you have to have air into the left side, X, and the right side, Y. So if you have air in here and air in there, you'll get air coming out, but not if you only have 1. You have to have 2. It's an AND gate. Okay. The way it works is kind of a little H-shaped assembly inside. So if air comes in one side, it actually blocks itself and can't get through. But it did open it up for the other side to get air through and then make its way out. All right. Something else you need to worry about in FIRST Robotics is flow control. When you've got those cylinders operating, they operate very, very quickly. They extend quickly and retract quickly. It can be kind of dangerous. And maybe more impact than you actually need. If you want to control the flow of air to make a cylinder move more slowly, you can use these devices. And this is a little flow control with a little screw top on the top. And through using a venturi, it actually constricts the air that flows through the pneumatics. Okay, so that's a flow control valve. Restricts the flow. And it usually does that by just having a little venturi that plugs up a hole. Another part to use quite a bit are those check valves, and the check valves only allow flow in one direction. They have a little, in this case, symbolized by this ball with a spring. So if you have air flowing in one direction, it flows through no problem. If you have air trying to flow the other direction, it blocks it. So check valves are kind of like diodes in effect. They only work in one direction. You can put a check valve and a flow control valve together in one unit, and it becomes a one-way flow control. Now in this particular circuit, the air will flow easily in the green direction. It'll flow easily downwards. But if you try to go the opposite direction, you can see the air is blocked and can squeeze through the venturi. So in one direction, there's restriction. In the other direction, it flows easily. This is a quick exhaust, so it's very similar to what we just saw. In that case, the air will flow one direction, but in the other direction, it actually gets exhausted straight to air. So if you have a cylinder that you want to extend through an actuator, but retract quickly, let's say a spring return cylinder, this guy, during a retraction, will allow the air to quickly vent through that little gray screen right there, little sound dampener. And it would retract much quicker because it doesn't have to go through the valve. The air can retract through there. So we don't usually use these quick exhaust valves in FIRST Robotics very much. So keep moving on. And that's your regulator. That regulator right here allows you to adjust the pressure of your FIRST Robotics device. You can see there by turning that knob, you can bring it up to any pressure you want. It measures it in bar, which is on the outside, 2, 4, 6, 8 bar. And on the inside, you can see it's measures it in pounds per square inch. And usually in FIRST Robotics, we like to keep it around 65 pounds per square inch. That's more than enough for our devices. This is a very sophisticated valve called a time delay valve. I'm not going to go into that. Basically, it just allows the circuit to operate on a time delay. And this is a pressure sequence valve, and it operates. It requires you to have one pressure active before the other pressure is allowed to work. So again, it's a bit above what I want to talk about in this particular talk. There's a pressure gauge, which you also have in your kits. You should monitor the pressure of your pressure tanks with this gauge in your FIRST robot. And this is the entire air service valve, so you can see everything all combined together. We got the regulator up at the top. We've got the pressure gauge. We've got the isolator switch for turning the air on and off to your system. The main air comes in this way. So your main air source, which I'll draw as a triangle, will come in this direction. And then you have what's called an FLR. This is a filter. It's filter, lubricator, and regulator. Now, we don't have to worry about lubrication. The old hydraulic pneumatic valves used to have a little oil in the air to lubricate them. But you do have to filter it because nonsense that comes in through this main air has to be cleaned out. So you just get nice, clean air proceeding. And any water, hopefully any water that comes spraying in there would be caught inside this little bowl right here. And you can drain it out from the bottom if that's necessary too. It's a filter, lubricator, regulator. Okay, and connected lines have a dot, and not connected lines have a little jump. So that's basically my little talk right now. I hope you guys got some information about the pneumatics and how that actually works. And if you want to talk to me later on or get in touch with me, there we go. This should work. You can just email me. I'm happy to answer any questions. Craig at frcwest.com. Craig at frcwest.com, and I'll be happy to give you any advice or hints or tips on using pneumatics. I'm going to put together another little quick video, which I'll upload in a little while, which will show how we're using pneumatics in one of our robot in 3 days machines that we used that we built a few months ago. So I look forward to hearing from you, and keep building, you guys, and keep in touch.